let's talk about modeling some of those future effects on climate. This is how we know what it's going to look like in 20 years, 50 years, 100 years. Granted, it has some uncertainty. It's just modeling. But that uncertainty, again, doesn't mean we don't know anything. One of the biggest tools we use to do this are called general circulation models, or GCMs. One of the biggest organizations that aggregates all of this information for use by different governments and by different corporations all around the world, by different people, is the IPCC. And then arguing with them tends to be an organization that has set itself up in opposition called the NIPCC. We'll talk about what those stand for in a moment. We'll talk about what consensus means and what scientists think, and the fact that we don't have consensus on every scientific idea, nor on climate change, not completely, but we have pretty overwhelming agreement. So not complete, just a lot. We'll talk about modeling the effects of temperature and precipitation and weather events, modeling effects on sea level ice, modeling some effects on biota, on organisms and where they live. And I'll mention briefly the possible existence of tipping points in Earth's climate. So these GCMs, general circulation models, are how we add together all the physical effects to predict changes in climate. So we use those equations to say, okay, given this much radiation, it'll warm up this much here. Given this much extra water vapor, we'll create this much cloud in this spot. Winds will push those clouds in this and that direction. So we put all of that math together in these huge models that are trying to represent what's going on over the entire climate. But we still have to grid them into relatively large boxes, right? Like you might have one box that's basically the size of a state, right? Because of how intensive these calculations are, you can't get too much smaller than that and still get a result in a human timescale. They also need some of the biggest supercomputers to run that we have, and a lot of our supercomputing power goes to things like these GCMs, in the same way that it goes to weather modeling too. So these models, as I'll say, they are imperfect because they have to have a coarse resolution, because they don't, they can't include every physical effect, because some effects are too small to increase, and some effects we just don't understand completely yet. But these models are also continuously being revised, and as we'll see, the models tend to have converged pretty well, where big changes are not expected as we tweak the knobs just a little bit here and there. The IPCC is the Intergovernmental Panel on Climate Change, and they put out lots of these assessment reports that summarize all this information. So I believe right now we're in the midst of the 6th assessment report being released. A lot of the information in this is from the 5th assessment report coming from 2013, right? And the IPCC has been arguing that humans are the dominant cause of current climate changes. It's organized by the United Nations, which puts some people off. It's got 830 lead authors, so 830 scientists that are really involved in this, but then also 1,000 or more other contributors that are reviewing this information, that are adding little bits here and there, that are pointing those lead authors in other directions, 2,000 reviewers to peer review some of that information, and they cite over 9,000 supporting papers. So, separate works that scientists or groups of scientists have done is where they're getting all that information. Now, set up in response to that has been an organization called the Non-Governmental International Panel on Climate Change, NIPCC, to match the acronym over there. And they are arguing that humans are not the dominant cause of current climate changes. I want to point out that there are some scientists that argue this. Organized by NGOs such as the Heartland Institute, it has 11 lead authors, 23 contributors, 78 reviewers, and 72 supporting papers. So the weight of evidence is a little heavier in the favor of the IPCC report. But if you are interested, you can always go and look at the NIPCC report and see why it is they think climate change is not caused by humans. You can also read responses to each of these. So there are, I just highlighted a couple here, and there are thousands that you could put. But some folks will argue against the IPCC. You can read some of those here. Some folks will argue against the NIPCC. You can read some of those there. So if you want more than just my opinion on it, definitely go to those places. I like to point out, though, some of the examples that like the NIPCC is trying to use to say that this isn't human-caused climate change. In particular, here's what they use to cite that it is the sun causing temperature change. They read two temperature series, one from the Sargasso Sea and one from South Africa. And you can read and hear exactly what those climate proxies are. One is organic matter in caves, and the other, I think, is one set of carbonate sediments. And they argue that because these two that they have, selected, or some might argue cherry-picked, show some remarkable similarities of pattern, right? Remarkable correlations, especially since the distances separate these two locations. And they're arguing that to say, oh, because those are really well correlated, they must suggest something real. So it must be, not human caused, because these aren't caused by human changes, because they're over the past few thousand years. Really, what they're saying here is because they see a correlation in two data sets that they really liked, that must mean that humans aren't the cause. Correlation does not equal causation. That's something that you probably have all heard at some point, that you need a preponderance of evidence, you need a mechanism, and you need repeated tests to infer that two correlated things are actually causatively related. So the fact that the NIPCC is just using correlation between two data sets out of 10,000 that the IPCC looked at is a bad sign. Okay, what is the consensus level on scientific agreement that humans are causing the majority of global warming? And so these studies have either asked scientists directly or analyzed their papers for their bulk conclusions, and found across all these studies that more than 90% of current climate scientists and more than 90% of current climate scientists agree that most climate change is anthropogenic. Plural of anecdote is not data, but I will say that my anecdotal experience with the professors that I've known is quite consistent with this. I've known lots and lots of geoscientists and climate scientists that agree and have studied climate change, and have found that climate change is very likely human caused, and almost all of it comes from humans. And only one or two scientists that are really tangentially related to climate change science that still argue that it isn't. They tend to be involved in other fields and not in climate science directly. Now, when the IPCC is considering what's going to happen over the next 100 or so years, they use several different emissions pathways. So 4 pathways in this case, for the 5th assessment report, looking at what would happen, if we stop today and we don't burn any other fossil fuels, which of course is going to have huge impacts on economies. So that's not going to happen. Versus other pathways where we use a little bit less fossil fuels, a little bit less, or we don't do any changes at all. So the main difference between these emissions pathways is how much humans are going to emit by burning fossil fuels, essentially. And we see that they find very big differences in these cases of how much carbon we're emitting. That's what this chart here is showing. So their lowest emissions pathway doesn't actually say that we stop right away, it just says that we taper it off to where we're essentially emitting 0 by 2100. Then their next pathway has us emitting less than half of what we're emitting today by 2100. Their medium high path has us continuing to increase, but eventually starting to taper off. And their highest pathway has us, going all out with fossil fuels through at least 2100. So when you see these colors, dark blue, light blue, orange to red, that's what this is going to correlate with, how much we expect humans to burn. And that's a variable. It depends on what we decide to do. When we look at what global mean temperature is probably going to do over that future, there's not a lot of difference, right, through like 2030. The colors are all sort of jumbled up there. But by 2050, we'll start to see large differences in temperature, depending on whether we decided to go all out burning it or we decided to really start to cut back. And those differences could amount to easily 1 Celsius or more by 2050. So a couple things that you want to know here. Warming will continue to 2050 and beyond, regardless of how much we cut emissions, because we've locked a lot of it in already. But it will warm more if we emit more. Let's talk about this thing that has come up sometimes, which are global warming pauses. Folks that don't think that climate change is caused by humans want to point to a lot of time periods when it seems like temperature has flatlined. So the most recent global warming pause was over about this range, maybe 2000 or a little before to about 2013, where temperature was relatively flat, very little increase. And so that average that we see there, which is the red line, was pretty flat during that period. A lot of folks were saying, "Oh, must not be humans because we're still starting to, we're keeping burning fossil fuels, but temperature has stopped increasing." Eventually, though, temperatures did start to spike again in 2016. So what do we think happened there? Well, we think that not all of the temperature was being diverted into the atmosphere, but we think that the oceans were storing a lot of that heat. And then, due to different ocean, circulation events and such that are really tough to get into, but basically the distribution of heat changes in between the atmosphere, the surface, and the ocean. We think that it started to release some of that heat that it had taken up, and so temperature dramatically spiked after that. So nobody's saying that there was a global warming pause after 2013, or at least they're being pretty disingenuous if they do say that. Here are some model results from the third assessment report versus this fifth assessment report. So, there's maybe, 15 years of climate model development in here. And you can see that the projections on top and on bottom have been pretty consistent as those models have been updated. At this point, we don't think that huge changes to those general circulation models will generate new predictions. We might get a little finer resolution on what we expect to happen. This shape here versus this shape here. But in terms of, suddenly figuring out that we're actually going to cool the environment, it's not going to happen. I also do want to point out that you can see on this graph, this is degrees Celsius change in a particular location versus degrees per 1 degree Celsius total change over Earth's surface. And so for every degree that we think all of Earth will warm, we think that, maybe a half a degree or a little more will be locked into the temperature in the oceans, but 2 degrees or more of change will happen in the Arctic. That is, the Arctic is projected to warm the fastest. IPCC projections of carbon dioxide, temperature, and sea level, so carbon dioxide, temperature, and sea level, have been pretty consistent, even from that first assessment report. And we have lowered the error bars on a lot of these, but our predictions have really been pretty consistent over time, suggesting that we have narrowed down on predictions that are not likely to change very much. And by 2100, and certainly beyond 2100, when we're all dead, probably, unless something dramatic changes in healthcare, global temperature is going to strongly depend on human emissions, and it will last for hundreds of years. If we really taper off by 2100, we might get to the point where we cool off below current temperatures today by the time that we hit 2300. But if we keep burning fossil fuels, then we're going to dramatically increase our temperature. And as you can see, on the high end, if we burn it all, global surface temperature change really could get by 2300 up to that 7 or 8 Celsius range, which, above this is when Antarctica melts. And that's 200 plus feet of sea level rise, maybe as high as 600 feet. So what's going to happen with precipitation? Because we talked about how temperature is going to change, not evenly across Earth's surface, but what about precipitation? Well, it's going to cause increases in precipitation in some spots. It's also going to cause increases in evaporation in most spots because it's going to warm up pretty much everywhere. So on average, we expect relative humidity and soil moisture, things that are important for crops, will decrease pretty much everywhere. So that's what we see in this here, right? We might have some soil moisture increases in a couple of areas, but for the most part, it's going to be decreases. Another impact that we're starting to think there might be a connection with is the jet stream. So the wobbliness of this jet stream, which is one of these global bands of air that circulates and drives big changes in weather. Like when we get, polar air coming through, it's because the jet stream wobbles downward, and that polar air is able to sort of intrude to the south over North America. If we get, really temperate weather during the winter, it's probably because the jet stream is high up, and so we can get sort of subtropical or tropical air coming in even during the wintertime. There are some thoughts that the jet stream is getting wobblier as climate change is occurring, and so we end up having more weird weather patterns throughout the year, and also more weather patterns that get sort of locked in. There was this big drought that happened when the jet stream got locked into its position over California for a couple of years, which could have caused that big California drought. Whenever you hear about polar vortex happening, we get that frosty air during the wintertime. That's probably a result of this jet stream being wobbly. It is naturally somewhat wobbly, but it seems like it's been getting wobblier. What about sea level rise? Any changes that we make are going to have little effect by 2050. So here's the sea level rise by 2050. If we burn a little versus if we burn a lot. So 0.24 meters versus 0.30 meters. Those are all about 1 foot of sea level rise. It's pretty much locked in at this point. But we can prevent another 9 inches or so by century's end. And that's not even accounting for possible tipping points like Greenland suddenly melting in a way that we don't expect, or the West Antarctic ice sheet melting in a way that we don't suddenly expect. We do think also that sea ice is going to continue to decline, even if we cut off. So if, 20 years from now, we have made a bunch of changes to our behavior, but it doesn't seem like climate is getting any better, this is why. We've locked in a lot of these changes for decades already. But if we change now, we can decide whether to stabilize that sea ice or melt it completely, depending on our emissions. Other things can be affected too. Surface pH of the ocean. So this is acidic. And this is what has changed today. We've dropped by about 0.1 pH units. And we could either stabilize that, or we could drop it by several more pH units over the coming 100 years or so. And that Gulf Stream current, the rate of that, is probably going to decline significantly if we make no adjustments. But we'll stabilize if we make large changes. What does that mean? Well, it's going to mean big changes to places in the Northern Hemisphere. And what about effects on biota? So this is a diagram of the expected range of a particular mosquito over time. So this is us, some fossil fuel burning versus lots of fossil fuel burning. And in this one particular example, we can see that it will have a really big effect on the range of that mosquito and how far north it goes, into the 2050s and 2080s. That happens for lots of invasive pest species, such as insects and fungi right now. It also, climate change is tending to push the ranges of both plants and animals northward while removing their summer extent, probably faster than they can move by planting new ones. So, trees, species could, quote unquote, migrate northward if, the climate change is slow enough that they can plant their seeds far enough north as they, as the climate changes. But we think that current changes are going on a little bit faster than that's possible right now. Same thing is going to happen to agricultural crops and ecosystems that humans rely on. I'll also point out that some proposed solutions to climate change in general, like using biofuels instead of fossil fuels, which involves, things like planting a lot of corn or sugar cane from which to get fuels, those can also have a detrimental effect on habitat extent and biodiversity. Not all solutions are as beneficial as each other, and they're all going to have some detrimental impact, whether on the environment or on us, via the economy in some way like that. So it's something to keep in mind. Lastly, I want to mention these tipping points, which are the possibility that we change irreversibly into a different overall climate state as a result of sudden, major positive feedbacks. We don't generally include these. And here are some options that people have somewhat speculated on, because it's hard to get information on something that's that sudden and that we don't have modern analog for. Because if we're looking at the nearest analog, we're looking 50 million years in the past to that PETM, which is a lot different than it is today, even if the rate of change is similar. We don't generally account for these possible tipping points. We do see some evidence that there were some tipping points, right? The Younger Dryas was a tipping point where we saw very dramatic sudden cooling in response to global warming, which also would have had huge changes on local ecosystems. So, we're not really sure what's going to happen. Is the Antarctic ice sheet going to tip and we're going to melt that whole thing really rapidly and suddenly have 8 feet more sea level rise than we expected? It's not, I wouldn't say that it's, more likely than not, but it is a possibility that we should consider.